Hello, welcome to this video about the FastFlood simulation platform. I'm here today to tell you a little bit about the different types of flood processes that we can model using this free and fast simulation tool that's available online at fastflood.org. Now, FastFlood can simulate flash floods, pluvial floods, but also coastal flood processes. In this video, we're going to focus on flash floods. Let's get started. First, we go to the website, and of course, we're going to start by thinking about the area that we want to model. Now, there's multiple options here. You can benefit from some of the global data sets that are linked to the tool and use these in your modeling. To define a model area, select the automatic download data button on the top left, as highlighted by the cursor. After clicking, drag an area to select a square model domain. Now for flash floods, where we want to do rainfall-driven modeling, I make sure to select a watershed or catchment, as that ensures that all of the rainfall that contributes to an event will actually also be included in the simulation. By default, global elevation datasets are available. If you're registered as well, you can find some additional ones, such as the Copernicus 30-meter elevation model, which is a bit higher quality and also available globally. Here I'm going to select this one at 20-meter resolution. After the downloading process, a shaded version of the elevation model becomes available. In its basic form, now we can go to the menu on the left side by clicking the menu button and then press Simulate to do our first simulation. Given that the area is not very large, we should instantly see our modeling results appear. Now, as we'll see in a couple minutes, we can add a lot more detail by describing various properties of the landscape with our own data or using global datasets. I do want to highlight that besides using these global datasets, we can also load our own elevation data. Let's have a look. If we open the menu again, using the menu button on the top left, under elevation, the only required input dataset for the model, though it's generally beneficial to use a couple more at least, depending on the processes that you're activating. Here we can also load our own elevation dataset. I'm going to select a new file under the elevation settings, and I'm going to load a file that's in the south of the Netherlands. This is the Geul catchment located in Limburg. I have a 40-meter resolution elevation model for this catchment that I can load and I can start to use for the modeling. Now, just to make sure that we see some of the spatial patterns in this catchment, I'm going to then simulate with all the default settings. Of course, there's a lot that we want to change to make sure that the settings are appropriate for this particular area. One of the first things we might want to do is select the rainfall settings. At the moment, the rainfall is set to the default value 30 millimeters per hour for 3-hour duration. This is a really significant storm event that's not really appropriate for this kind of climate and context. So we have to specify our own precipitation event here. Now we can do so in a couple ways. One of the easiest ways is to do our own analysis based on station and observed precipitation data. We can then fill in the rainfall intensity and the rainfall duration. There is an additional helper tool available here by clicking on the graph icon. After clicking this, we can load a comma-separated value file which contains our rainfall data. And the model will automatically give us information about the appropriate duration in hours and mean precipitation rates during the event. We can select the percentage of the total precipitation that should be at least included in this analyzed rainfall event. By changing this percentage and pressing the Analyze button, we can select a smaller cumulative amount but higher central peak of the precipitation event to use in our modeling. Typically, we see that values between 70 and 90% work well for this kind of modeling. Now, of course, this is a larger area where we might want to input a rainfall map. And the station that I showed you here was actually located in the north. On average, I know that for this area, 10-hour precipitation event with a rough intensity of 0.2 millimeters per hour represents the actual dynamics of the precipitation here in the summer of 2021. If I press simulate again, we can see our results appear quickly. Besides precipitation, there's a couple other processes that are really relevant to add to your simulation. One of them is land cover information. Land cover determines the friction that the water flow experiences during the movement. We can use the built-in automatic download tool to load world cover 10-meter resolution land cover data. The model will automatically assign appropriate Manning surface roughness coefficient values that describe the frictional forces experienced by water flow based on this global dataset. And then for the user, it's as simple as clicking the download button, and the tool will automatically grab this data and fill in all that's needed for the model domain. As you can see, the various classes have their Manning surface roughness coefficient automatically assigned based on literature accepted values. Another important process that we want to include is infiltration. During a storm event, a large percentage of the water typically infiltrates into the ground instead of becoming overland flow and eventually accumulating to floods. By pressing the infiltration settings, we see there's quite some options here to mess around with. For now, I'm going to choose the automatic download functionality again. Here, the tool is automatically going to go towards the SoilGrid's global soil properties database and estimate infiltration rates based on this. Again, by clicking the download button, it will go into these global datasets and prepare for us automatically the infiltration rates that we need. A major effect of this is that the flood impact and the flood volumes during the simulation will significantly decrease because a percentage of the water will infiltrate instead. When we're modeling at 40-meter resolution, it's not always the case that the channels, in this case the channels of the Geul River, are well represented in the elevation data. The river here is quite small, and we might want to include it separately as a subpixel property. Now there's some automatic tools here that will help us do this. We can estimate automatically the channel dimensions for this area based on the drainage area of the channel at each point. Now there's some default relationship based on global channel and river dimensions. And these relationships can be useful, but typically you want to have your own values filled in here or make your own relationships. These relationships take the form of a power law, and for this area, the typical values that you can use are 1.1 and 1.05. By activating the channels automatically, their dimensions will be estimated during the simulation and used automatically to produce better flood estimates. We've added now a couple input data sets and processes to the simulation. We added elevation data, land cover information, precipitation, infiltration, and channels. We can also ask the model to produce more output for us. One of these outputs is discharge. Under the general settings, located at the bottom of the menu, we can find the output discharge estimates in flow network setting. By selecting this and simulating again, we can also view the discharge map. This allows us to see the discharge routing that's used internally within the model. Furthermore, we can also use the Shift button to inspect hydrological values, such as the elevation, the flood depth, the discharge, and other properties, such as channel dimensions. Now, at the moment, the simulation is not calibrated, and that's usually an important process of flood modeling. What we're going to do here is do some calibration for this area. There's multiple types of observational data that we can use for calibration. The first one that we're going to add here is peak discharge. This is the peak flow rate in the channel. Now for the Geul here, observations have led to the estimation of a peak flow rate of 110 cubic meters a second. So we can press the right mouse button, go to the Add Observation option. A marker appears. When we click it, we get the option to specify certain observational input points for the model. Now at the top it says we can select known peak discharge. So let's select this option. Finally, we can provide the value below as 110 cubic meters a second. In addition, we can also load flood extent observations. Now for this area, a detailed flood extent map was produced after the event based on drone imagery. I'm going to the Calibration tab under the settings, and there I can select a new file from my disk describing a geotiff containing flood extent. This map should contain the same size, the same extent and number of pixels as my elevation model, but contains 0 values where no flood was observed and 1 values if there was a flood observed. I'm going to go ahead and select the file that I have prepared containing the observed flood extent. This observed flood extent is then also overlain on top of the model results. We can now calculate the error directly, and we'll see already that our model is having a 97% accuracy. However, the simple pixel count based accuracy metric is typically not such a good indicator of accuracy for a flood model. The reason for this is that empty areas that are predicted to have no flooding by both the model as well as the observations are typically more plentiful than those with floods. So even an empty prediction will have relatively high accuracies, typically above 90%. Cohen's kappa, the C value above, provides a more critical reflection of the accuracy of the model. And here it's only 0.58, where a perfect model score would be 1. Now we can tweak the parameters in the model, such as the infiltration, using the infiltration multiplier value, for example, or the land cover, surface friction, using the multiplier provided there as well to carry out our calibration work. But the model also includes an automatic calibration functionality. If we click on the up arrow next to the Simulate button, we can find a couple options, one of which is the automatic calibration. If we click on this, we get a pop-up asking us which processes we want to use in our calibration. In this case, I'm going to activate Manning's surface roughness coefficient and the infiltration rate. By activating both and using the default number of variations for each parameter, between 50% and 150% of their original value, the model will automatically carry out 36 simulations for each unique combination of these two parameters for me. And in the end, it will tell me about the optimal setting in terms of parameters to achieve accurate model output. At the bottom, we can find our Calibrate button, after which the model will start to run automatically for 36 times until it can show us the optimal model results. Since the model is quite fast, 36 simulations should finish here in a matter of 20 seconds in total. Of course, when you activate more processes and more parameters, you might need hundreds of simulations to carry out a full calibration. Still, that should be able to finish within several minutes. The 36 simulations has finished, and we can see that our model has found optimal parameter settings for our simulation. It's indicating that our infiltration rates should significantly be increased, and that we're currently underestimating the infiltration during the event, as well as that the Manning surface roughness coefficient should be about 30% higher over the area in order to make the model match with observational data. We can then go back and fill in these values in our multipliers for these processes. So on the land cover, I'm going to select 1.3 as our multiplier value. For infiltration, I'm going to select our 1.5 value. Then, using the up arrow, I can go back to just simulate my current scenario. Finally, we can verify the behavior of the model by loading a observed flood outline. Under the viewer options in the settings, under overlay flood extent, we can select a GeoJSON file. I have prepared such a file containing the flood extent for the region. The blue outline here represents the observed flood extent that was observed during the 2021 floods in the south of the Netherlands. As we can see after calibration, our match between the flood extent and the observed flood extent is really high quality. A lot of this depends also on the resolution and detail in the elevation model. The quality and the patterns here are mostly to thank to the National Dutch Elevation Model, which provides a high accuracy representation of terrain data. Once you have a calibrated model, you can also go ahead and run alternative scenarios. Within the rainfall settings, we also provide a link with global weather analysis data. Here we can automatically download design storms. These are statistically representative storm events that describe the precipitation that you can expect with a certain probability. By clicking the button Download Design Storm, we get a dialog asking us for our desired return period and duration. We can also view all of the data related to the weather analysis to see full IDF curves and general extreme value distributions for the area. For now, I will select a 10-year return period storm with 12-hour duration. By pressing the download button, the tool will automatically go into these global datasets based on the ERA 5 global weather analysis data and give us a precipitation duration and intensity that matches the 10-year return period, 12-hour duration storm event. This process can take a little bit, but at the moment it's already done. There's additional tools to also adjust these extreme precipitation events to climate change based on the climate scenarios of your choice. This is also globally available and based on the CMIP6 Global Climate Model Ensemble. Besides altering the hydrological processes and properties, you can also introduce mitigation to simulate alternative scenarios. Some things you might do, for example, is implement alterations to the elevation model that might represent reservoirs or levee systems. These can also be polygons, squares. You can also add discharge boundary conditions, paint elevation differences directly, add culverts or channels, or look at changes to surface and land use. For now, we can experiment with a flood barrier within the city. Simply by drawing it, we can introduce this into our simulation. After running, we see that the results are directly incorporated in the resulting flood map. By specifying the height, we can also change the structure and the design of this. Besides running and calibrating and editing scenarios to use in a flood model, we can also look at more detailed simulation. At the moment, we're running the model at 40-meter resolution. This helps us for such a large catchment to have interactive simulations that run rapidly, but we might want to go to higher resolution. Now there's a couple of options here. We can load an elevation model at higher resolution for the entire area. That's certainly possible, although that might slow down the simulation to take 5 or even 10 seconds. Another option is to use the Refinement tool. We can specify a second model domain by using the plus button in the top left. I've already done so, and I'm going to select the second model domain by pressing the 2 icon that has appeared. Once I've done so, I can select an elevation model for this area or use the global datasets. Make sure that the model domain that you're using is in the same coordinate system as the one that you used in your first domain. That is required if you want to use the refinement tools. For now, I'm going to use a 5-meter elevation model for the city of Valkenburg. Instead of running a separate hydrological model here, I'm going to use the upscaling settings in the menu. By selecting input from other area, and in the drop-down menu selecting our first model domain, the model is going to take the results from our first simulation, which does the entire catchment, and use this to refine it and redistribute the water on a physical basis and provide high-resolution output for this local area. By pressing Simulate, we can see that the results are automatically adapted to this higher resolution. Do note that there are limitations to this kind of refinement approach. For example, we can, in this particular refinement setup, not draw mitigation into this simulation. Instead, we have to go back to our original simulation and implement the mitigation there. Then rerun the second model domain in order to get the results in the higher resolution detail as well. Thank you so much for watching this video. I hope you found it useful. If you have more questions, please visit www.fastflood.org. And if you go to the documentation, you can find many more tutorials related to the functionality of the website. Thank you.